use L'Hopital's rule to find the following. Now, L'Hopital's rule says if we get something that's indeterminate, either 0 over 0 or infinity over infinity, the limit of that function will be the same as the limit of the derivative of the top over the derivative of the bottom. So in this first example, if I plug 0 in, I get sine of 0 divided by tangent of 0. That is 0 over 0, which is indeterminate. So I can use L'Hopital's rule. I take the derivative of the top using the chain rule. So I got cosine of 3x times 3. And then I also had to use the chain rule to take the derivative of the bottom. Derivative of tangent is secant squared. Derivative of 5x is 5. Now I'm going to try plugging in x equals 0. 3 times cosine 0, that's 3 times 1, or 3. Secant squared of 0 times 5. Secant squared of 0 is 1, so 5 times 1 is 5. And I'm left with 3/5. In my second example, we're finding the limit as x goes to 0 from the right of sine x to the tan x. That is 0 over 0, or 0 to the 0, when I plug in x equals 0. This is actually indeterminate as well. However, if I want to use L'Hopital's rule, I have to somehow rewrite this as a quotient. L'Hopital's rule only works when you have fractions of the form 0 over 0 or infinity over infinity. It does not work in any other case. So there's a little trick you can use anytime you have an exponential function that you're trying to find the limit of. I'm going to think of my problem as y equals limit sine of x to the tangent of x. Then I'm going to take natural log of both sides. So natural log of y is the limit as x goes to 0 of natural log of sine x to the tangent x. Again, I took natural log of both sides. Then there's a property that says we can take that tan x, that exponent, and we can move it down. That's one of my properties of logarithms. So now I've got natural log of y is limit of tan x times natural log of sine x. If I plug in 0 now, I get tangent of 0, which is 0, and natural log of 0, well, there's an asymptote there. The natural log function goes down to negative infinity. 0 times negative infinity is still indeterminate. However, if I want to use L'Hopital's rule, I have to rewrite this as a quotient. So multiplying by tangent x is the same thing as dividing by 1 over tan x. And I'm actually going to rewrite that 1 over tan x as a cotangent x, just because it looks a little bit nicer. Finally, if I plug in my 0, natural log of 0 is still negative infinity. There's an asymptote there. Cotangent of 0, that is also undefined. There's also an asymptote there, and it goes to infinity. Finally, this is a case where I can use L'Hopital's rule, infinity over infinity. So I'm going to take the derivative of the top and the derivative of the bottom. I have to use the chain rule to find the derivative of the top. Let's see, natural log of sine x. So we're going to get 1 over sine x times cosine x. And then the derivative of cotangent x is negative cosecant squared. All right, so again, I have my derivative. It's 1 over sine x times cosine x. That turns into a cotangent x. And negative cosecant squared x in the denominator. Now I'm going to do a little bit of simplification with this and then see if I can actually plug in the x equals 0. So cotangent is the same thing as dividing by tangent. It's the same thing as 1 over tangent x. So I'm just going to rewrite that cotangent x as a tan x on the bottom. And then cosecant is the reciprocal of sine. So dividing by cosecant is the same as multiplying by sine. And so I'll just put a negative sine squared x on the top. Now, if you try plugging in x equals 0 here, you still get 0 over 0. That's indeterminate. You could use L'Hopital's rule again. You're allowed to continue using L'Hopital's rule. but I'm going to just do a little bit more simplification. We've got a negative sine squared x divided by tan x. That's dividing by a sine over cosine. Or, copy dot flip, multiplying by a cosine x over sine x. And then I can actually cancel one of those sine x's out. So if I cancel one of those sine x's out, I'm just left with a negative sine x cosine x. So I was actually able to reduce my derivative all the way down to negative sine x cosine x. Finally, when I plug in x equals 0, I get 0 times 1. Sine of 0 is 0, cosine of 0 is 1. 0 times 1 is 0. Almost done. That's not my final answer. Remember, this was natural log of y. We're trying to find y. If natural log of y is 0, y has to equal e to the 0, or 1. And so my final answer to this problem, this limit equals 1.